to draw the molecular orbital energy diagram for any period 2 homonuclear diatomic molecule or molecular ion, all you need to do is put electrons in boxes, okay? But you have to know how many electrons you're putting in boxes and what order to fill the boxes in and what the boxes are, okay? So for any element up to group 15 or below, you're going to use the MO diagram on the left. The only difference between the two is the relative ordering of the pi2p and the sigma 2p here and here. Okay, because the pi2p is lowered in energy for the first half of the P block elements. Okay, so that's the only difference between the two, but you need to make sure you select the right one. If you're in period 16 or above, you're going to use the one on the right. Okay, so make sure you get the right ordering. Okay, so these diagrams come from overlap of atomic orbitals to form one bonding and one anti-bonding molecular orbital. Okay, so two atomic orbitals combine to form two molecular orbitals. So for the 1s, that's the sigma 1s and the sigma star 1s for the bonding and the anti-bonding. Same for the 2s, the sigma 2s and the sigma star 2s. Now, when you are overlapping your 2p orbitals, you've got three 2p atomic orbitals coming from each atom forming the bond, so that gives you a total of 6 molecular orbitals that you are forming. The sigma ones come from linear overlap between the bonds, so there's one sigma for each bonding and anti-bonding, and then the pi's, there are going to be 2 degenerate pi orbitals coming from the overlap in front and behind and above and below the bonding axis. That's why you get 2, right, from the py and the pz if we're defining px as the bonding axis, okay, and those are degenerate. So remember, we've got to fill the molecular orbitals according to the Aufbau principle, okay, same as we did for atomic orbitals, which means you fill from the lowest energy available orbital first, and then Hund's rule, which says if you've got degenerate orbitals, you're going to singly occupy each of them first with one single parallel spin electron, and then you also have to account for the Pauli exclusion principle, which is if you have to pair electrons up in a molecular orbital, they're going to have opposite spins. So we're going to still stick to those principles just like we did for filling atomic orbitals. So if we have a molecular ion, I would treat it just like a homonuclear diatomic atom. So first of all, write the electronic configuration for each atom that's coming together to form the bond. So nitrogen will be 1s2, 2s2, 2p, 3, right, just coming straight from the periodic table. So that is a total of 7 electrons that one nitrogen is bringing to the party. But you've got 2 nitrogens, right? So you've got 2 of those coming together, sharing their atomic orbitals to form molecular orbitals. So N2, then the molecule has 14 electrons that we've got to put in molecular orbitals. Now, if it is N2 plus, has lost an electron to get that -1 charge, okay, so we're going to subtract an electron off the total, so we should have a total of 13 electrons for N2 plus, okay, so we're going to select the MO diagram on the left, and we're going to start filling it up from the bottom, okay, so 1, 2, 3, 4, 5, 6, 7, 8. Now watch very carefully the order I do this in. 9, 10. Look how I followed Hund's rule. We have single occupation of each of those pi2p degenerate orbitals before we pair up. 11, 12, and then the 13th is going to go into the sigma 2p. So that's what my MO diagram should look like. Now, a little bit of a word to the wise, okay? Technically, you don't have to count the 1s part. Why? Because this is core electrons down here. It's a closed shell, right? Because that would be your helium 1s2 configuration. The equivalent for molecular orbitals would be a sigma 1s2, sigma star 1s2, right? That would be the same as a closed core configuration. These are your valence electrons. So sometimes you might only see people do this top half, and that's fine. I'm just being really thorough because this is the diagram that ALEKS gives you. So I want to make sure that you are not being like 4 electrons out in your final count because you didn't count the ones that it's also shown on the diagram. So that also means that if you were discounting those core electrons, you wouldn't add these 1s2 electrons to the count. So instead of putting 13 electrons in your molecular orbitals, you'd only be putting 9 in there, right? So just as an FYI. Okay, so I think we should do another one of these, just because I know it's a lot to sort of get used to. Okay, so let's try and pick something where we use the other one so I don't have to erase what I've already done. And that's going to be easier said than done now, right? I want something in group 16 above. Come on, give me something in group 16 above. I know I should pause this, but now I'm kind of committed. Okay. The O2 molecule, okay, and iron would have been more fun, but here we are. Beggars can't be choosers. All right, so we're asked to write the MO diagram for the O2 molecule. It seems it's just a molecule, not a molecular ion. I might as well go and show how we could also fill up the atomic orbitals as well. Just for completion, so 1s2, 2s2, coming straight from the periodic table, 2p4. So oxygen has 8 electrons. Okay, so when we first arrive as in class, and if you're doing this in exams, like you might not want to take the time to do this, you could actually fill in the total number of electrons coming from oxygen in your atomic orbitals to kind of warm you up for your molecular orbitals, right? So we're happy with Hund's rule that we'd singly occupy those 2 p's, 1, 2, 3, and then the 4th would have to pair up, okay? And you do that for each of your oxygen atoms, right? Oh, that's kind of got a bit wrong. Spin up, spin down. So then you would be able to toss up, I know they're not quite straight, but how many total electrons you should have in the O2 molecule. So that is going to be 2 times 8, which is 16 electrons. Okay, there's no charge associated with that. It's not an ion. If it was an anion, you'd have to add electrons to that and to know how many you'd have to put in your MO diagram, etc. All right, so just to avoid confusion, I am going to change my pen color for the molecular orbitals for oxygen. So I'm going to put 16 electrons in. So start at the bottom, work your way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then breathe carefully. 11, 12, single occupation to the pi 2p's. 13, 14, pair them off, and then 15, 16. Those